Welcome. If you're passionate about power systems, substations, transmission lines, and everything that drives the world of electricity, you're in the right place. Here, we break down complex electrical engineering concepts into simple, practical, and engaging explanations. Whether you're a student, professional, or just curious about how electricity powers our world, these videos will help you learn and stay updated. So stay connected with the world of electrical engineering. Here, I am going to discuss the vector diagram of a voltage transformer. From that, we will see how the error comes in the potential transformer, how the ratio error, meaning voltage ratio error, comes, and how the phase angle error comes into the picture. So this is E1. E1 is the voltage that is induced across the primary of the voltage transformer. It is not actually the supplied voltage. It is the voltage that will be induced across the primary winding when the primary is connected to the live system. Without drawing the supply voltage first, meaning the input voltage first, we have drawn that induced voltage, which we will understand later. Now, just imagine that this is the induced voltage across the primary winding and this is the no-load current. That means it is the vector sum of the magnetizing component and the core loss component, and that will not be exactly 90 degrees lagging from E1. The angle between E1 and I0 will be a little less than 90 degrees because of its loss component. Now, let us connect the burden with the secondary circuit of the potential transformer. For that, the primary current starts flowing through the primary winding also, and say that is I1 dash. I1 dash is not the total primary current flowing through the primary winding when the burden is connected. It is the current that exactly reproduces the secondary current, say I2. So the total primary current taken by the potential transformer from the supply is I1. That is the vector sum of I0 and I1 dash. Now, as I1 is the total current flowing through the primary winding, there will be a primary resistance drop, and that will be I1 R1. Due to the leakage reactance of the primary winding, there will be a reactive voltage drop, and that will be at 90 degrees from the direction of the resistive drop. That will be represented as JX1 I1. If we add these three, E1, I1 R1, and JX1 I1 vectorially, then we will get the actual voltage that has been supplied to the primary winding from the system, and that is V1. So the voltage we are applying across the primary terminal of the PT is V1, not E1. V1 is the applied voltage, and after the inductive and resistive drops, a voltage will appear across the primary winding. That voltage will be exactly equal to the induced EMF across the primary winding, which is E1. Now say this is E2. What is E2? E2 is the induced voltage across the secondary winding of the potential transformer, and that will obviously be exactly 180 degrees apart from E1 because E2 is purely induced across the secondary winding of the potential transformer. Now we will draw this line parallel to I2 because I2 is the current flowing through the secondary winding. That will be the secondary resistive drop, which is I2R2. In the secondary winding, there is also inductive reactance. So for that, there will be another voltage drop, which will be drawn as JX2I2. Now we will connect this gap, and this line represents the actual voltage appearing across the secondary terminal of the voltage transformer when it is connected to the meter, which is V2. So E1 by E2 is the actual transformation ratio according to the turns ratio of the potential transformer. That is N1 by N2. But it is not exactly equal to V1 by V2. Therefore, V1 by V2 is not exactly equal to N1 by N2, and that causes the ratio error in the potential transformer. The ratio of induced EMF across the primary and secondary gives the actual turns ratio of the PT. But externally, the input voltage is V1 and the output voltage is V2. So we will observe that we are supplying V1 voltage and we are getting V2 voltage. V1 by V2 will be the practical voltage ratio of the PT. Obviously, there is a difference between these two ratios, and that difference causes the turns ratio error. Now draw a dashed straight line. This is exactly 180 degrees apart from the applied voltage V1. So V2 must be along this line, or the reverse of V2 must be along this line when the voltage transformer is ideal. But due to the presence of reactance, resistance, loss component, and magnetizing current in the potential transformer, V2 has diverted an angle theta from that dashed line. This diversion of angle is known as phase angle error. We represent the turns ratio as K. So V1 over V2, N1 over N2 equals E1 over E2, and that is K. So E1 over E2, V1 over V2 divided by V1 over V2 into 100% gives the percentage ratio error. E1 slash E2 is K. So K minus V1 slash V2 divided by V1 slash V2 into 100% equals KV2 minus V1 divided by V1 into 100%. That means the secondary output voltage multiplied by the turns ratio minus the primary input voltage divided by the primary input voltage into 100% is the turns ratio error as per the formula given in the standard. Thank you. Thanks for watching. We hope this video helped you understand electrical engineering concepts better. If you enjoyed the content, don't forget to like, share, and leave your thoughts in the comments. Stay with us and stay updated with more videos on transmission lines, substations, and power systems. Until next time, stay curious, keep learning, and keep the power flowing.